The moon is Earth's only natural satellite and its closest neighbor in space. The moon most likely formed when an object the size of Mars collided with our planet billions of years ago. This catastrophe turned Earth into a molten sphere and ejected a huge chunk of matter into orbit, which cooled and took on a spherical shape. Now, the crater-ridden sphere revolves around our planet, causing tides in the oceans. The moon's size is just over a quarter of Earth's size, making it the fifth largest natural satellite in the solar system. The moon has several phases, such as new moon, full moon, crescent, first and last quarter. But no matter the phase, our neighbor is hard to confuse with any other cosmic object in the night and sometimes even daytime sky. But imagine you wake up at night and see that the moon doesn't look as usual. It seems brighter and larger. However, in a half-sleep state, the changes aren't so noticeable. You go back to bed, not even suspecting that Mercury has taken the moon's place. The surface of Mercury, the closest planet to the sun, resembles a lunar landscape. It is dotted with meteorite craters. In size, Mercury does not exceed 2/5 of Earth's size. Nevertheless, it is slightly larger than the moon, and that is why the planet would have a greater impact on Earth. Nights would become brighter, tides would intensify, as would ebbs. The lunar cycle, the period during which the moon, or to be precise, Mercury, passes through all its phases, would become 14 hours shorter. But overall, such a replacement would not radically affect the state of our planet. What about Venus? What if, instead of our familiar satellite, the third brightest natural object after the sun and moon took its place? Venus is often called Earth's sister because their mass and size are almost identical. In our sky, Venus would be as large as Earth observed by the Apollo crews from the moon's surface. The morning star would shine much brighter than the moon. Firstly, the planet reflects 6 times more sunlight. Secondly, it would occupy at least 16 times more space. That is why nights on Earth would become as bright as early twilight. If you looked at Venus, you would notice indistinct swirling patterns on its yellowish-white cloud cover. Venus would not become Earth's satellite. Most likely, both planets would revolve around their common center of mass, and this orbit would be quite strange. If Venus moved at the same speed as the moon, the planets would collide in the near future. Well, it's time to move on. If Mars took the moon's place, you would definitely notice it, thanks to the reddish disk and the planet's size, which is twice that of the moon. You wouldn't even need a telescope to admire the unusual color and dark spots enhancing the planet's surface. And even if you didn't pay attention to the red planet, you would definitely feel something was wrong. Mars is half the size of Earth, but several times larger than the moon. If a small cosmic object is replaced by a larger one, it will disrupt the delicate balance. If you are unlucky and Mars replaces the moon and you find yourself on the coast, you would have to evacuate urgently. Under the influence of the planet, powerful waves would rise, crashing onto the shore like giant tsunamis. Mars would reflect more sunlight than the moon. Nights would become brighter, and earthly landscapes would acquire an eerie reddish tint. But with a telescope, you would be able to admire Olympus, the highest mountain in the entire solar system. Mars is not large enough to radically change Earth's orbit, but over time, the two planets would surely begin to revolve around each other, creating a double planet system. And if Mars seems so close, travel to it would become a reality. It's time to think bigger. If Jupiter took the moon's place, Earth as an independent planet would cease to exist. It would become a satellite of the largest planet in the solar system. But there's good news. In such a case, people would have the opportunity to see a sky of stunning beauty. Jupiter is incomparably larger than the moon, and the giant striped sphere would stretch across the entire visible horizon. You would be able to admire the yellow, brown, red, and white clouds floating in Jupiter's atmosphere, if you had time for it. Alas, the gas giant's gravity would immediately lead to earthquakes, volcanic eruptions, and tsunamis. The Earth's crust and mantle would begin to be pulled towards Jupiter, and Earth would be torn apart. The planet would be compressed and stretched in different directions by 90 meters. Unfortunately, Earth's speed is only 10% of the speed necessary to remain in Jupiter's orbit. For this reason, in less than a day, our planet would crash into the gas giant. But let's not dwell on the sad. If Saturn were in place of the moon, it would be an unforgettable sight. The planet is more than 35 times larger than our satellite. The golden sphere would occupy 18 degrees of the sky, and the famous rings would stretch from horizon to horizon. Earth would be slightly further from the gas giant than its satellite Dione. Since Saturn is much more powerful than our planet, Earth would turn into its satellite. Unfortunately, Earth's rotation speed would not be enough, and in a couple of days we would crash into Saturn. But before reaching the planet's atmosphere, we would have to pass through its exquisite rings. They consist of pieces of comets, asteroids, and shattered satellites. The journey would be far from easy, and we must not forget that Earth would have to bypass Saturn's satellites, and there are 53 of them. But what if a collision did not happen and Earth became the 54th satellite? Then the gas giant's gravity would lead to powerful tectonic shifts across the globe, the planet's crust would tear apart, and eventually nothing would be left of it. Also, not a very positive outcome. Both Uranus and Neptune are ice giants. They are roughly the same size, larger than Earth but smaller than Saturn and Jupiter. Both planets are covered in ice and boast a beautiful green-gray hue. If one of them replaced the moon, the consequences would be the same, so let's flip a coin. Okay, let's see what happens if one day you see Neptune in the sky. Neptune is 14 times larger than the moon. The planet would look like a huge, bright blue balloon, not only during the day, but also at night. It would seem to you that Neptune is 15 times larger than the sun, and you would regularly observe solar eclipses. After the sun disappeared behind Neptune, our planet would plunge into complete darkness for more than an hour and a half. Neptune's mass is 17 times greater than Earth's mass, and its gravitational pull is much stronger, so our planet would become a satellite. Yes, again, and it would orbit Neptune at a slightly greater distance than its largest moon, Triton. By the way, in such a case, Earth would eventually risk colliding with this cosmic object. But let's assume we were lucky and did not encounter any of Neptune's moons. However, we would have enough problems even without that. Waves on Earth would become 1,000 times more powerful than with the moon. Neptune's gravitational force would not tear Earth apart, but would heat our planet. Seismic activity would gradually increase, causing earthquakes and volcanic eruptions, and we would probably lose internet. Draw two parallel horizontal lines in your imagination. Now connect them at any points in two different ways. A vertical line that goes straight up from the bottom line to the top, and a diagonal line. Which one is shorter? Of course, the vertical one. This is the shortest way to connect the top and bottom lines, and it's the most basic answer to our question. It's simpler and faster to get into orbit in a straight line. The bottom line is the Earth's surface. Our planet is a complex mix of all sorts of matter combined into an impressive mass of almost 6 sextillion tons. That's like 6,000 billion billions. A lot of zeros in short. Essentially, all this mass acts like a giant magnet, which, among other things, allows Earth to maintain what we all know as the atmosphere. The top line is the boundary of Earth's atmosphere. Everything above it is planetary orbit and outer space. But the atmosphere itself is also filled with matter. It's a combination of gas with its own density. When launching a shuttle, all this gas constantly presses down on it, causing friction and greatly slowing it down. Passing through a vacuum is like cutting through air, whereas passing through the atmosphere is more like trying to push through grape jelly or strawberry jelly. It takes a lot of energy and force to get through it, all while experiencing the pull of the huge gravitational magnet called Earth. Airplanes don't suffer as much from passing through the atmosphere because they use its density to lift off the ground and maintain altitude. Two things help them with this: engine thrust and wing shape. Airplane wings cause the air in front of them to split into two streams. Naturally, the streams try to rejoin behind the wings, but their shape makes the upper stream flow faster. The faster the air moves, the more density it loses. This means that the stream passing under the wing is denser than the upper one. This creates a gradual lift for the plane. Essentially, wings allow planes to glide through the air. Of course, this would be impossible without a huge force pushing the plane forward. That's what thrust is for. Just to get off the ground, planes need to develop enormous speed. The required speed depends largely on the type of aircraft. 60 miles per hour for light aircraft and approximately 150 miles per hour for airliners. To just take off and climb to an altitude of 3 kilometers, a Boeing 747 requires just under 3 tons of fuel. This may sound impressive, but let's look at the space shuttle. The first thing that catches the eye are the cute, tiny, short wings, which would be useless in a horizontal takeoff. On the other hand, more massive wings would be useless in the vacuum of space, and it would also be difficult to make them strong enough to withstand launch. The space shuttle's small wings serve only one purpose: safe landing so that the craft can be used in future missions. Their size only needs to be enough to prevent the shuttle from spinning uncontrollably during its descent through the atmosphere and to bring it back to Earth, as the engines are not used during landing. The space shuttle's engines are completely different from an airplane's engines. An airplane's engines need air from the atmosphere to operate. Obviously, the shuttle's engines don't need it, as atmospheric air is hard to find in space. That's why shuttles use rocket engines. To see what rocket means in this case and how it all works, simply inflate a balloon and let it go. It will spin around until it runs out of air, and all that time it will be moving in the opposite direction to the escaping air. To lift off, a rocket engine must produce enough thrust and burn the necessary amount of fuel. In reality, a space shuttle requires so much fuel during takeoff to achieve the necessary thrust that it couldn't manage with just 3 engines. It requires 2 additional solid rocket boosters and a separate huge fuel tank that is jettisoned in the final stage of launch. And a shuttle can only reach orbit with sufficient power. The power of a shuttle with 3 engines and 2 boosters is about 3.5 million kilograms of thrust. To provide such a powerful push, the external tank contains about 725,000 kilograms of rocket fuel. And to control the flight, these 3 engines must have an astonishingly complex design. But would it be possible to launch a shuttle into orbit if we redesigned it to use the atmosphere as airplanes do? Unfortunately, the answer is no. Even more fuel would be needed to maintain the necessary speed along a diagonal launch trajectory. The fact is that even if an airplane reaches the upper atmosphere, Earth still won't let it go. To exit the atmosphere, any object taking off from Earth must be fast enough to cross the point of so-called escape velocity. This is needed to overcome the planet's gravitational pull and allow the object to enter orbit. Our planet's orbital velocity is 28,000 kilometers per hour. Obviously, this is much higher than the speed of sound, and many, many times the cruising speed of an airliner. Now try to imagine a plane flying that fast. How much fuel would it need? Moreover, it would have to be strong enough not to break into pieces. The cost and complexity of the technology would simply be unrealistic. The likelihood that shuttles may become a thing of the past has prompted scientists and engineers to find better solutions for reaching orbit and beyond. One such idea suggests that in the future, people will ascend into space on a giant space elevator. The space elevator is a concept of a huge tower extending to a satellite in orbit that moves in sync with Earth's circular motion. The tower's height should be about 35,400 kilometers, and it should be made of an incredibly strong material, carbon nanotubes. Platforms inside the tower are planned to be driven by electromagnetic propulsion machines. The journey from Earth to the satellite would take only 5 hours. Such a mega structure would allow faster and safer travel to space. But carbon nanotubes proved not strong enough to build such a huge tower, so the search for the ideal material is still ongoing. Another project using a similar approach is called the Space Tram. The structure needed to launch the project is not as large, but still impressive. It is a vertical vacuum tunnel that will push the shuttle using levitating magnetic propulsion. Air will not be able to slow it down, and electromagnetic force will push it through the tunnel and accelerate it until the shuttle breaks into the sky at a speed close to escape velocity. Such a shuttle will weigh less because it will not need to carry a lot of fuel. But still, nothing is said about how a human would endure such acceleration, because upon arrival, the crew could turn into pancakes. If such ideas sound strange to you, and they do, get ready for the last one. It is possible that people will use airplanes to ascend into orbit. No, I wasn't lying to you. An airplane itself cannot go into space, but it can act as a launch platform. Even better, a special airplane will be created for this purpose, with a wingspan of almost 122 meters and capable of climbing to an altitude of more than 10 kilometers. Small shuttles launched from such an airplane will not have to pass through a large layer of the atmosphere. It will be easier for them to overcome Earth's gravitational pull. Richard Branson is already working on this solution in the Virgin Galactic program to take tourists to the edge of space.